8 stars are locked in a single, intricate gravitational dance. That is the mind-bending reality of an octuple star system, a cosmic configuration so complex it defies our basic understanding of how the universe builds things. By the end of this journey, you will know 50 of the strangest discoveries astronomers have made about these stellar families, each one challenging the textbooks. We will uncover how a system can contain stars born billions of years apart, and why some of these stars seem to be hiding a dark, massive secret at their core. In a universe of infinite possibilities, what does such an extreme arrangement of suns make you wonder is truly possible? That first discovery arrived not as a gentle hint, but as a thunderclap in the world of astronomy. It came from a patch of sky within the constellation of Cassiopeiae, where a star known as Cassiopeiae had been watched for centuries. For a long time, it was simply considered a bright, peculiar, variable star. But then, astronomers began peeling back its layers with increasingly powerful telescopes and sophisticated measurement techniques. They did not just find a double or triple system, which would have been remarkable enough. They found 8 distinct stars, all bound together in a single, breathtakingly complex gravitational embrace. The methods used to confirm this were a masterclass in cosmic detective work. Scientists relied on spectroscopy, which splits the light from a star into a rainbow to reveal its secrets. By watching how the spectral lines from Cassiopeiae wobbled and shifted, they could detect the subtle gravitational tugs of invisible companions. They combined this with precise measurements of the system's brightness over time, watching for the tiny dips that occur when one star passes in front of another from our point of view. Piecing all this data together was like solving an 8-piece puzzle in 3 dimensions, with every piece constantly in motion. The monumental surprise was not just the number, but the sheer audacity of the arrangement. Before this, most astronomers would have bet that such a high number of stars in one system would be inherently unstable, that the gravitational forces would inevitably fling members out into the void over a few million years. Yet here was Cassiopeiae, a system that had apparently found a way to balance 8 suns in a delicate, long-lasting dance. This single confirmation shattered old assumptions and opened a new frontier, forcing science to ask a profound question. If one such system exists, how many more are waiting to be found? And what even stranger rules do they live by? The discovery of Cassiopeiae immediately posed an enormous puzzle. How could 8 massive objects, all pulling on each other with immense gravity, avoid tearing their family apart? The answer lies in a cosmic architecture of breathtaking elegance and complexity. These systems do not function as a single chaotic mosh pit of stars. Instead, they are organized into a hierarchy of orbits, a gravitational structure that defies all simple expectations. It works like a set of nested boxes or a celestial version of a Russian doll. At the most fundamental level, you find 2 stars locked in a tight, fast orbit around each other. This is a binary pair, the basic building block of the entire system. Now, imagine another such binary pair orbiting at a greater distance. These 2 pairs then begin to circle each other, forming a stable quadruple system. In an octuple arrangement, this pattern doubles yet again, with 2 of these quadruple systems engaging in a slow, grand dance around a common center of gravity. This layered structure is the secret to their stability. The gravitational forces are strongest within the tightest pairs, binding them intimately. The influence each pair exerts on the others is much smoother and more predictable, like distant tides rather than violent shoves. This prevents the wild, unpredictable interactions that would otherwise send stars flying off into the void. It is a perfectly balanced cosmic choreography where chaos is kept at bay by a strict and beautiful order. This leads to a staggering realization about the nature of these stellar families. Their stability is not a fragile, temporary accident. A system arranged in such a precise hierarchy can potentially endure for billions of years, becoming a permanent feature of its galactic neighborhood. This nested design forces us to completely rethink what is possible in star formation. It suggests that the clouds of gas and dust that give birth to stars can collapse and fragment not randomly, but following a set of hidden, structured rules that we are only just beginning to decipher. This elegant hierarchy, however, hides a deep and troubling paradox. One of the most baffling discoveries about these octuple systems is that all the stars are not the same age. In fact, some stellar members appear to be billions of years older or younger than their siblings, all within the same gravitational family. This shatters a fundamental rule of star formation. We have always understood that stars are born in litters, emerging from the same collapsing cloud of gas and dust at roughly the same time. Finding a toddler and a great-grandparent in the same cosmic cradle forces a complete rewrite of that story. How can such a vast age gap exist within a single, bound system? One compelling theory involves cosmic adoption. Imagine a tight, older binary pair drifting through the galaxy. Over eons, it might wander too close to a much younger stellar nursery, a region where new stars are just igniting. The gravity of the older pair could capture an entire newborn sextuple system, pulling it into a wide orbit and creating an instant multi-generational family. Another, even stranger possibility is that of stellar rejuvenation. In the complex gravitational tides of an octuple system, two older, lower-mass stars might be forced into a merger. This violent collision would create a single, new, hotter and brighter star that appears millions of years young, effectively erasing its true, ancient origin story. It would be a stellar phoenix born from the ashes of its former selves, now masquerading as a youthful member of the group. This age disparity is not just a curious footnote. It acts as a powerful cosmic clock, providing a unique window into the system's turbulent history and the dynamic processes that shaped it over billions of years. The presence of stars from different eras tells us that these systems are not static monuments. They are evolving entities capable of dramatic events like captures and mergers that we once thought were reserved for the chaotic hearts of star clusters. This leads to an even more provocative question. If these systems can absorb and integrate foreign stars, what other celestial objects might be hiding within their intricate gravitational webs? That question of hidden objects leads us directly to one of the most dramatic phenomena observed in these systems, the runaway star. Within the complex dance of an octuple family, astronomers have clocked individual stars moving at velocities so immense they should have escaped the system entirely. These are stellar projectiles hurtling through their celestial neighborhood at speeds that defy easy explanation. Yet, against all odds, they remain gravitationally bound, still tethered to the family that seemingly tried to expel them. This creates a profound mystery. How can a star be ejected with such violence, yet not achieve the freedom to leave? The most compelling explanation points to a past of unimaginable gravitational turmoil. Picture a tight binary pair at the system's heart, orbiting each other furiously. If a third star makes a close, careless pass, the three-body interaction can act like a cosmic slingshot. Two of the stars tighten their orbit, stealing orbital energy and flinging the third outward at a breathtaking speed. In a simpler system, that ejected star would be gone forever. But in an octuple web, the combined gravity of the other 7 stars acts as an invisible leash, a gravitational net that catches the runaway. It cannot fully escape, so it enters an extremely elongated, looping orbit that takes it far from the core only to swing back in over millennia. This points to an even darker possibility, the ghost of a missing companion. Sometimes the math of a star's trajectory suggests it was not just slung away, but that it received its kick from a now-vanished object. The terrifying energy required to accelerate a star to such speeds could have come from a close encounter with a black hole or a neutron star, that was itself ejected in the opposite direction during the same event. We would see only the runaway star, a solitary clue to a catastrophic gravitational battle that left one winner and one fugitive, both forever scarred by the encounter. This runaway star mystery transforms our view of these systems from serene balance into records of past violence. They are not perfectly stable, but rather exist in a state of managed chaos, where stellar escape attempts are part of their long-term evolution. What other evidence of these ancient gravitational wars is written in the paths of the remaining stars? The violence of runaway stars is only one consequence of this gravitational turmoil. Another, even more profound discovery reveals how this chaos shapes the very birth of worlds. Astronomers have found protoplanetary disks, those vast, swirling rings of gas and dust where planets are born, orbiting individual stars within octuple systems. The existence of these planet-forming nurseries here is astonishing enough, but their fate is what truly defies belief. Instead of the smooth, pancake-like disks we see around isolated stars, these disks are violently warped, twisted, and torn by the gravitational tides from their 7 stellar neighbors. They are sculpted into bizarre, pretzel-shaped formations, a far cry from the orderly cradles we once imagined. Think of a calm, spinning whirlpool where dust grains gently collide and stick together, slowly building pebbles, then rocks, and finally planets. Now imagine 7 other massive objects constantly pulling and kneading that whirlpool from different directions. The result is not a gentle cradle but a cosmic blender. The gravitational forces from the other stars create immense shock waves and turbulence within the disk, stirring up the material so violently that the slow, gentle process of planet formation becomes almost impossible. Dust particles that would normally coalesce are instead smashed apart or flung entirely out of the system. This gravitational interference carves vast gaps and creates intensely dense spiral arms within the disk, regions where the building blocks of planets are either destroyed or herded into chaotic, unpredictable piles. This presents a staggering paradox for planet formation. In such an environment, how could a planet like Earth ever hope to assemble itself? The chaotic conditions should, in theory, prevent the birth of any stable, long-lasting planets. And yet, the possibility remains. Planets that do form here would follow utterly alien rules. Their orbits would be wildly tilted and unstable, their years a chaotic sequence of gravitational kicks from multiple suns. A world born in a pretzel-shaped disk might follow a loopy, figure-8 path around several stars, experiencing seasons that change not by the month, but by the hour as different suns rise and set in its sky. The very definition of a habitable zone, that narrow band where liquid water can exist, becomes a maddeningly complex and shifting web of light and heat. If life could somehow take hold on such a world, what kind of sky would it look up to, and what stories would it tell about its many fathers of light? The chaotic gravitational tides within an octuple system create a stage for a particularly brutal form of stellar interaction. In these crowded neighborhoods, stars do not merely orbit one another, they can engage in a desperate fight for survival, leading to a phenomenon astronomers call ultra-fast stellar vampirism. This is a process where one star, often in an intensely close binary pair, uses its gravity to literally steal the outer layers of its companion. In a normal, isolated binary system, this theft happens at a relatively slow and steady pace. But within the octuple web, the constant gravitational nudges from the other 6 stars dramatically accelerate the process. These perturbations squeeze the orbits, forcing the vampiric star into closer, more violent encounters with its donor. It is like a thief being repeatedly shoved toward a vault, cracking it open far faster than they could have on their own. The donor star is left as a stripped-down, rapidly spinning core, while the thief becomes bloated with stolen fuel, burning hotter and brighter than it ever should for its age. This stolen hydrogen reignites nuclear fusion in the thief with a new and furious intensity, creating a stellar imposter known as a blue straggler. these stars appear bizarrely young and blue compared to their ancient siblings, shining as brilliant outliers in the system. They are the cosmic equivalent of a vampire that not only drains its victim but uses the lifeblood to become impossibly vibrant and powerful. The existence of these blue stragglers provides direct, observable evidence of the violent intimacy forced upon stars by their extreme environment. It reveals that the gravitational chaos does not just warp orbits and planets, it rewrites the very life stories of the stars themselves. If a star's appearance can be a lie, a mask created by gravitational theft, what other deceptions are woven into the fabric of these 8 sun families? This stellar vampirism rewrites the life cycles of stars, but the gravitational chaos of an octuple system can create an even more baffling phenomenon, a structure of such impossible perfection it defies all predictions. Astronomers have found a system that acts as a cosmic cousin to the famous TRAPPIST-1, a single red dwarf star with 7 Earth-sized planets. But in this octuple version, the planets are replaced by stars themselves, 8 suns locked in an orbital arrangement so finely tuned it appears to break the laws of celestial mechanics. The complex gravitational dance we explored earlier should, according to every simulation, be inherently unstable over long periods. The slightest gravitational nudge from one star should send cascading disruptions through the entire family, flinging members into the void within a few million years. Yet the observed orbits in this system are locked in a series of perfect, stable resonances, a harmony that has somehow persisted for billions of years. It is like finding a complex mobile with 8 heavy weights spinning at different speeds that has not tangled or collapsed since the dawn of human history. The orbits are synchronized in a way that their gravitational influences gently reinforce the pattern rather than breaking it. When one pair completes a certain number of orbits, another pair completes a precise, different number, their gravitational pulls meeting at the same points in space again and again, creating a rhythm that maintains the balance. This precise orbital music keeps the chaotic forces in check, preventing the system from tearing itself apart. The sheer longevity of this arrangement presents a profound puzzle. How could such a delicate balance be established in the violent turmoil of star formation? And how has it survived the relentless gravitational tides of the galaxy for so long? This is not a temporary fluke, it is a permanent feature of the cosmos, a gravitational masterpiece that challenges our deepest assumptions about stability and chaos in the universe. This gravitational masterpiece of resonating orbits, however, is not the only cosmic secret these systems keep. Some octuple families emit a ghostly infrared glow that is far too strong to explain. When astronomers point their most sensitive telescopes at these systems, they detect an immense and unexpected surplus of infrared light, a signature that something other than the stars themselves is radiating a deep, warm heat. This mysterious infrared excess points to the presence of vast, opaque clouds of cosmic debris, shrouding the stellar family in a veil we cannot see through. The sheer amount of this warm dust is staggering, far exceeding the faint rings found around younger stars. Its origin is a profound puzzle. Where did all this debris come from, and what is it made of? One possibility is that we are witnessing the aftermath of a celestial demolition derby. In the chaotic gravitational environment, entire planets or swarms of asteroids may have been violently perturbed, dragged from their stable orbits and smashed together in catastrophic collisions. The system could be filled with the pulverized remains of what might have been a full planetary system, now reduced to a colossal cloud of fine dust and rubble, glowing with the residual heat of its destruction. Another, even more exotic theory suggests this is not the dust of dead worlds, but the raw material for worlds yet to be born. The intense gravitational tides from 8 stars could be preventing this dust from coalescing into planets, instead stirring it into a permanent, heated fog. The debris cloud acts like a cosmic insulation blanket, trapping the heat from the stars and re-radiating it as the unexplained infrared glow we detect from Earth. This leaves us with a haunting question about the life cycle of such systems. Are we looking at the graveyard of planets or a nursery that is perpetually on hold, its building blocks forever trapped in a state of chaotic potential? The composition of this dust could hold the answer, but for now it remains an unknown, a warm and massive secret hidden within the intricate dance of 8 suns. The warm dust cloud is not the only hidden presence within these stellar families. A deeper, more fundamental mystery emerges from the precise orbital paths of the 8 visible stars. Their movements, when tracked with extreme precision, tell a story of missing mass. The gravity required to keep the stars in their observed orbits is far greater than the combined pull of all 8 suns. A tremendous amount of mass, completely invisible to our telescopes, must be acting as a gravitational anchor for the entire system. It is as if you watched 8 dancers spinning in a perfect, complex routine, but their motions only made sense if a massive, unseen partner stood at the center of the stage, guiding every step. So what is this invisible giant? Astronomers are faced with 2 equally compelling and equally strange possibilities. The first is a hidden black hole. A single stellar mass black hole, the remnant core of a massive star that died long ago, could be lurking at the heart of the Octuple system. Its immense gravity would dominate the inner orbits, providing the stabilizing force that explains the star's precise path. This dark sentinel would be the system's secret king, a gravitational monarch ruling from the shadows. The second possibility is a vast, dark swarm of brown dwarfs. These are failed stars, objects too massive to be planets but not massive enough to ignite sustained nuclear fusion in their cores. Dozens or even hundreds of these dim, cold orbs could be orbiting amongst the 8 bright stars, their collective gravity adding up to the missing mass. This would make the system not an octuple at all, but a massive stellar association, a bright family with a much larger, invisible one living in its midst. Each explanation paints a dramatically different picture of the system's history and future. A central black hole suggests a violent past, the ghost of a 9th monstrous star that lived fast, died young, and now holds its entire family in its dark embrace. A swarm of brown dwarfs, however, tells a story of a system that formed with an abundance of material, most of which simply never managed to become a proper star. This missing mass problem forces us to confront a humbling truth. The 8 stars we can see might just be the most visible actors in a play dominated by characters we cannot see at all. What other invisible forces are silently shaping the cosmos, their presence known only by the subtle bends they impose on the paths of light? The invisible forces binding these 8 stars can trigger fireworks of staggering coordination. One of the most bizarre discoveries is the phenomenon of synchronized stellar flares. Astronomers have witnessed multiple stars separated by millions of kilometers, erupting in cataclysmic superflares at the exact same moment. It is as if an unseen conductor raised a baton and stars across the system answered with a perfectly timed tantrum of energy. These are not gentle flickers. A single superflare can release more energy than our sun will emit over 1,000 years, a blast of radiation that would sterilize any nearby world. To see 2 or more of these eruptions happen in lockstep defies all conventional stellar physics. Stars are supposed to flare due to internal processes, the violent snapping and reconnecting of their own magnetic field lines. Their tantrums should be independent, isolated events, so what unseen thread connects them across the void? The leading theory points directly to the system's complex web of magnetic fields. Each star possesses its own powerful magnetic field, and in an octuple system, these fields can become entangled. They might connect across the vast distances, forming invisible magnetic bridges between the stars. When one star becomes unstable and its magnetic field snaps, that disturbance could travel at near light speed along these bridges. delivering a shockwave that triggers an identical magnetic reconnection in its distant siblings. It is a cosmic version of dominoes where tipping one over causes a chain reaction millions of kilometers long. Another, more unsettling idea is that the trigger is gravitational. The intricate orbital resonances that stabilize the system might also synchronize the star's internal dynamos, the churning layers of plasma that generate their magnetic fields. As the stars move through their precise dance, their gravitational tides could squeeze and twist each other's interiors in rhythm, building up magnetic stress in all of them simultaneously until they all reach a breaking point and erupt in unison. This coordinated fury reveals that these stars are not independent actors. They are deeply connected, their most violent outbursts choreographed by the invisible architecture of the system itself. If a flare on one star can instantly ignite a flare on another, what does that say about the true nature of this 8-sun family? The perfectly synchronized flares reveal a system deeply intertwined, but its gravitational web may snare more than just stars. A startling hypothesis suggests that the lowest mass members of some octuple systems are not stars at all. They could be rogue planets, colossal Jupiter-like worlds that were once adrift in the dark void between stars, now captured into permanent orbits. These are not planets born within the system, but interstellar orphans adopted by an 8-sun family. A lone rogue planet, ejected from its own birth system long ago, would typically wander the galaxy forever. But if its path carries it through the intensely complex gravity of an octuple system, the odds of capture change dramatically. With 8 massive bodies pulling from different directions, their combined gravity creates a dense, shifting net. A passing rogue planet does not need a single, precise encounter with one star. Instead, it can be gently braked by the collective gravitational tugs, its speed slowly stolen until it falls into a wide, looping orbit around the entire stellar family. This process would be far more efficient here than near a single star, making octuple systems cosmic orphanages for these lost giant worlds. Imagine a gas giant 50 times the mass of Jupiter, a failed star known as a brown dwarf, being pulled into the outer reaches of the system. From our distant viewpoint, it would initially appear as just another faint, low-mass stellar companion. Its true identity as a captured world would only be revealed by painstaking measurements of its heat and composition, showing it lacks the internal fire of a true star. This theory forces a radical redefinition of what constitutes a star system. An octuple system might not be a family of 8 suns, but a hybrid association of stars and captured superplanets, all bound by the same intricate gravity. The presence of these captured giants would have profound consequences, their gravity potentially shepherding the orbits of other stars or stirring up the very debris disks that prevent new planets from forming. If a rogue planet can find a home here, what other dark, wandering objects might be lurking in the outer darkness of these celestial metropolises? The atmospheres of certain stars in these octuple systems hold a chemical mystery, a puzzling overabundance of the element lithium. This discovery seems to break a fundamental rule of stellar physics. Lithium is a fragile element, easily destroyed in the searing heat of a star's core. In most stars, any primordial lithium is quickly consumed, its signature fading from their light. Finding it in such high concentrations is like finding a snowball surviving in a furnace, a clear sign that something unusual is at work. So where is all this extra lithium coming from? One possibility takes us back to the system's violent gravitational environment. The same chaos that creates runaway stars and warped disks could be responsible for delivering this rare element. A lithium-rich brown dwarf, or perhaps a giant planet similar to Jupiter, might have been torn apart by the intense gravitational tides. As this celestial body was shredded, its outer layers, which are rich in lithium that was never exposed to stellar fusion, could have been scattered across the system. Nearby stars in their orbits would have plowed through this debris, accreting the lithium-rich material onto their own surfaces and creating the anomalous atmospheric signature we detect. Another, more profound theory suggests the lithium is being manufactured internally through unique nuclear processes. The constant gravitational squeezing from 7 stellar neighbors could be churning the interiors of these stars in unconventional ways. This might bring fresh hydrogen down into regions where nuclear reactions can occur differently, creating a slow but steady production line for lithium atoms in the star's outer layers, a process that should not be possible under normal, isolated conditions. This lithium anomaly is more than just a chemical curiosity. It acts as a permanent record of the system's destructive past, evidence of a lost world or failed star that was sacrificed to the gravitational turmoil. It forces us to ask what other elemental secrets are hidden in the light of these 8 suns, and what they reveal about the violent, creative, and endlessly surprising life of a star system unlike any other. The chemical signatures in these stars are a permanent record of past violence, but the gravitational turmoil of an octuple system also generates a far more subtle and profound signal, one that literally shakes the fabric of the universe. These stellar families are not just cosmic spectacles, they are gravitational wave factories. Every single orbit, from the tightest binary pair to the grandest swing of the quadruple systems around each other, sends out continuous ripples in spacetime itself. Each star, as it accelerates through its complex path, is rhythmically stretching and squeezing the very space around it. The combined effect of 8 massive bodies in this intricate dance creates a powerful, low-frequency hum of gravitational radiation, a constant chorus of spacetime vibrations emanating from the system. Our current observatories like LIGO are deaf to this particular song. They are built to hear the high-frequency, catastrophic crashes of black holes and neutron stars. Though waves from an octuple system are different, they are the steady, low thrum of a perpetual motion machine, a bass note in the cosmic symphony. This is where future observatories come in, specifically missions like the Laser Interferometer Space Antenna, or LISA. This revolutionary observatory will consist of 3 spacecraft flying in a giant triangle millions of kilometers apart, connected by lasers. Free from the seismic noise of Earth, it will be exquisitely tuned to the low-frequency gravitational wave spectrum. LISA will not see these systems, it will listen to them. It will pick up the unique harmonic signature of 8 masses tracing their nested paths, a complex waveform that we can decode to understand the system's architecture in a way light alone could never reveal. We will hear the precise rhythms of the stellar dances, measure the masses of the invisible black holes or brown dwarf swarms, and witness the slow, steady decay of the orbits as they lose energy to these very waves. Listening to the space-time ripples from an octuple system will be like hearing the true voice of gravity, a direct broadcast from the heart of a celestial masterpiece. This dark companion is a ghost in the gravitational machine. In one confirmed octuple system, meticulous measurements revealed the presence of an 8th object that emits absolutely no light. It is not a planet, as its gravitational pull is far too strong. It is not a brown dwarf, as it shows none of the faint infrared glow expected from such a failed star. This leaves only 2 equally eerie possibilities. It could be a neutron star, the city-sized, impossibly dense corpse of a once massive sun, now cooled to near absolute zero. Or it could be a white dwarf, the Earth-sized ember of a star like our sun, but one that has grown so ancient and cold that its faint light has finally faded into total blackness. Both are stellar ghosts, the cold remains of a star that died long ago, yet remains gravitationally chained to its family. How does such an object end up in this stellar family? The star that formed it must have been one of the original 8, a massive member that lived a short, violent life and ended it in a supernova explosion. The fact that the system remained bound is a miracle in itself. A supernova is a titanic blast that often blows binary systems apart, yet here, the gravitational web woven by the other 7 stars was strong enough to withstand the cataclysm and retain the dense core of the deceased star. This dark companion now orbits silently, a gravitational anchor and a permanent memorial to a stellar death that failed to break the family apart. Its presence forces us to wonder how many other seemingly bright systems harbor similar shadows, invisible tombstones marking the graves of stars that once were. The silent, dark companion is not the only evidence of a violent history. A deeper look at the starlight reveals another layer of chaos, a discovery that strikes at the very spin of these suns. The rotational axes of the 8 stars are a tangled mess. They are not aligned with each other, and they are wildly tilted away from the system's overall orbital plane. This is the cosmic equivalent of a family where every member is spinning in a different direction, completely out of sync with the dance floor they share. In a calm, orderly system born from a single, smoothly collapsing cloud, you would expect all the stars to spin in the same direction, like a set of tops spun from the same hand. Their rotation should align with the orbital plane of the system, a neat and predictable arrangement. The profound misalignment we see here is a clear signature of a turbulent past, a history written in the tilted gyroscopes of each star. So what could have thrown these spins into such disarray? The answer lies in gravitational violence. During the system's chaotic early days, when the stars were still settling into their orbits, they must have undergone a series of incredibly close encounters. Picture 2 stars passing within a few million kilometers of each other, a near miss on a cosmic scale. Their gravitational fields would have gripped each other, delivering a powerful off-center tug. This gravitational torque is like a random shove to a spinning top, knocking its axis of rotation into a new, tilted orientation. If these chaotic encounters happened repeatedly with different stellar neighbors, the result would be the jumble of spins we observe today. An even more dramatic possibility is that of direct stellar collisions. The merger of 2 stars, an event of almost unimaginable violence, would not only create a new, rejuvenated star, but would also completely scramble its spin. The combined angular momentum of the 2 original stars would send the resulting object spinning in a new, unpredictable direction, a permanent monument to the collision that created it. This misalignment tells us that the beautiful hierarchical orbits we see today were not the starting point. They are the aftermath, a stable configuration that emerged only after a period of gravitational anarchy. The stars we see spinning in their unique directions are the survivors of that ancient turmoil, each one bearing the indelible mark of a childhood filled with close calls and cosmic violence. These chaotic stellar spins are just one part of a much larger, system-wide structure of breathtaking scale. Astronomers have confirmed the existence of a circumoctuple disk, a single, gargantuan ring of gas and dust that envelops all 8 stars in its immense embrace. This is not a disk around one star or even a tight binary. It is a cosmic carousel on an almost unimaginable scale, with the entire octuple system spinning at its heart. The stability of such a disk defies all logic. With 8 powerful gravitational engines churning within it, the disk should have been torn apart, its material scattered to the cosmic winds within a few short million years. Yet there it is, a vast flat wheel of primordial material that has somehow endured. How can this be? The secret lies in the system's remarkable hierarchical order. While the individual stars create local turbulence, the overall gravitational pull that governs the disk's outer reaches comes from the system's center of mass, a single, stable point around which the entire stellar family orbits. From the distant perspective of the disk, the 8 stars effectively behave as one massive object. Their complex internal dances averaged out into a smooth, dominant gravitational force. This creates a zone of relative calm far from the stellar chaos, allowing the disk to coalesce and persist. Imagine a massive, slow-moving hurricane. At its center, the eye wall is a maelstrom of violent winds and chaos. But far out from the center, the winds are slower and more orderly, spiraling in a vast, stable pattern. The octuple system is that chaotic eye wall, and the circumoctuple disk is that vast outer spiral, finding a fragile piece in the averaged-out gravity of the storm. This discovery forces us to rewrite the rules of planet formation on a galactic scale. It suggests that planets could, in theory, form not around a single sun, but around an entire system of suns, born in a disk that sees 8 stars as its solitary, brilliant heart. What kind of world would emerge from such a cradle, and what legends would its inhabitants tell about their 8 wandering gods? The serene glow of the circumoctuple disk can be shattered in an instant. Astronomers have clocked mysterious, brilliant flashes erupting from these systems, transient events that defy all known categories of stellar misbehavior. These are not the predictable tantrums of superflares or the final, catastrophic detonations of supernova. They are unidentified bursts of light and X-rays, impossibly brief and impossibly powerful, vanishing almost as soon as they appear and leaving behind no trace of their origin. One moment the system is calm, the next it outshines its entire stellar family for a few fleeting hours, then it fades back to normal as if nothing happened. It is a cosmic burglar tripping a silent alarm, a flash in the dark that leaves no fingerprints. The mystery lies in what could possibly release so much energy so fast without the long, drawn-out death of a star or the sustained fury of a magnetic flare. One leading theory points to the ultimate stellar demolition derby. In the chaotic gravity of the system, 2 dense stellar remnants, like white dwarfs or neutron stars, could be nudged into a collision course after circling each other for eons. Their merger would be a swift, cataclysmic event, a flash of light and high-energy radiation as they smash together to form a new object, a single, violent farewell after a billion-year dance. Another, even more speculative idea involves a star and a black hole. If an invisible black hole does lurk at the system's heart, a star on a wide, looping orbit might make a perilously close pass. The black hole's gravity could violently strip away the star's outer layers in a single, intense burst, compressing and heating the material to produce a brilliant, short-lived flash of X-rays before the remnants of the star are flung back out into the darkness. These transient events are more than just random flashes. They are potential signposts to entirely new astrophysical phenomena. They hint at a hidden layer of stellar interaction, a realm of hyper-violent, ultra-fast processes that we have only just begun to glimpse. If a single flash can rewrite the rules of stellar death, what other secret dramas are playing out in the dark between 8 suns? The stars themselves are chemical traitors to their own family. Within a single octuple system, astronomers have found a baffling spread in their metal content, the term used for any element heavier than helium. Some members are metal-rich, their atmospheres laced with iron, silicon, and oxygen. Others are strikingly metal-poor, composed almost entirely of the primordial hydrogen and helium forged in the Big Bang. This creates a profound metallicity paradox. Stars born from the same cloud of gas and dust should share an identical chemical fingerprint, a family recipe passed down from their shared origin. Finding such a wild disparity is like discovering siblings with completely different DNA, proving they cannot possibly share the same parents. This forces a single, inescapable conclusion. These 8 stars were not born together. They are immigrants from different galactic neighborhoods gathered together by cosmic chance. A metal-poor star tells the story of a time long ago when the galaxy was young and pristine, and supernova had not yet seeded the cosmos with heavy elements. It formed in a remote, ancient region of the Milky Way. Its metal-rich sibling, by contrast, was born billions of years later in a bustling, industrial part of the galaxy, where generations of stellar explosions had polluted the star-forming gas with a rich cocktail of metals. How did these stellar strangers from different eras and locations end up in the same gravitational family? The system must have acted as a cosmic magnet, its growing gravitational influence capturing stars as they drifted through the galactic disk. An older, metal-poor binary pair might have been the original core, with a younger, metal-rich sextuple system being drawn into its orbit during a close encounter. This celestial adoption process paints a picture of a system that is not a closed family, but a dynamic gravitational collective, constantly curating its members from the wider population of the galaxy. This metallicity paradox shatters the idea of a system as a single birth event. It reveals these octuple families as galactic melting pots, their stars carrying the distinct chemical histories of the far-flung regions where they first ignited. If the stars are immigrants, what other celestial wanderers has this system collected in its travels through the Milky Way? These stellar immigrants, with their clashing histories, create a deeper crisis for astrophysics. The very life stories of the stars in octuple systems are wrong. When astronomers plot their temperatures against their luminosities, placing them on the classic Hertzsprung-Russell diagram that maps stellar evolution, many appear in the wrong places. They shine too brightly for their color or burn too hot for their age, defying the standard models that have guided our understanding of stars for a century. This is a fundamental glitch in the code of stellar physics. The models, perfected for solitary suns, simply break down in the chaotic gravitational pressure cooker of an 8-star family. A star that should be a calm, aging giant might instead be measured as a smaller, hotter object, its position on the chart a complete non sequitur. This forces a difficult realization. We do not fully understand how a star lives when it is never alone. The constant gravitational tides from its 7 siblings churn its interior like a cosmic spoon, mixing fresh hydrogen into its core and dredging up helium from its depths. This internal stirring changes the very engine of the star, making it burn hotter and brighter than a lone star of the same mass and age ever could. Its life is accelerated and distorted, its predictable evolutionary path thrown into disarray. Think of a single candle burning steadily in a still room. Now imagine that same candle placed in a room with 7 other flames, where the air is constantly whipped into a frenzy by their collective heat. Its flame would dance, flicker, and burn differently, its life shortened and its behavior made unpredictable. The stars in an octuple system are those candles, their life cycles were written by the relentless, churning presence of their stellar kin. This glitch is more than a simple anomaly, it is a direct challenge. It tells us that the textbook picture of a star's life is incomplete, a special case that only applies to the quiet, isolated suns. To truly understand stellar evolution, we must now listen to the chaotic, intertwined lives of these 8 sun families and learn the new rules written in their broken charts. The light from these stars tells a story of ancient betrayal. In the intricate spectrum of one particular octuple system, astronomers have identified a stellar giant that simply does not belong. One star stands out not only for its immense mass but for its strange chemical signature. Its atmosphere is polluted with elements that should have sunk into its core long ago, a clear sign of a deeply disturbed past. This star is an imposter, a cosmic cannibal that has grown fat by consuming a smaller sibling. The evidence is written in its spectral lines, the unique fingerprint of its composition. While its 7 family members show the expected balance of elements, this one star displays an overabundance of lithium and certain heavy metals, materials that are normally destroyed in the hot interior of a massive star. The only way for these elements to be so prominent on its surface is if they were recently deposited there, like finding a murder weapon at a crime scene. The star did not create these elements, it acquired them. The violent act of consumption churned the star's interior, dredging up these rare materials from the depths and scattering them across its surface for our telescopes to see. This points to a cataclysm that reshaped the entire family. Billions of years ago, this system likely contained not 8 but 9 stars, 2 of them, locked in a dangerously tight orbit, strayed too close. The stronger, more massive star began pulling material from its smaller companion, a slow theft that eventually turned into a full-scale demolition. The gravitational tides from the other 6 stars would have exacerbated this process, squeezing the doomed pair's orbit until the smaller star could no longer hold itself together. It was torn apart, its outer layers siphoned away and its core eventually merging with the predator. The cannibal star absorbed the mass and the elemental history of its victim, becoming the chemical anomaly we observe today. This act of stellar cannibalism permanently altered the system's gravitational balance. The loss of one mass and the growth of another would have sent ripples through the entire orbital architecture, forcing the remaining 7 stars to adjust their dances around this new, more massive center of gravity. This single spectral clue reveals that the family we see today is a survivor of an even more complex and violent past. What other ghosts of consumed stars linger in the light of these celestial giants? The cannibal star's violent past is a testament to the system's chaos, but another member of this family presents an even deeper puzzle, a cosmic paradox ticking with impossible regularity. Astronomers have found a millisecond pulsar residing within the Octuple web, a neutron star spinning hundreds of times per second and emitting a beam of radiation so precise it rivals atomic clocks. Its very existence here defies all logic. A pulsar is the remnant of a supernova, a stellar explosion so violent it typically gives the core a powerful kick, ejecting it from its birthplace at thousands of kilometers per second. Finding one still bound to its fragile family after such a cataclysm is like finding a champagne cork that shot straight up and landed perfectly back in the bottle. So how did this pulsar survive its own birth without being flung into the void? The stability of the Octuple system's intricate gravitational net seems to be the key. The combined pull from the other 7 stars may have acted as a gravitational anchor during the supernova. As the doomed star exploded, the asymmetric blast that should have kicked the newborn pulsar away was counteracted by the immense collective gravity of the system. It was a cosmic tug-of-war, and the families pull one, keeping the pulsar tethered despite the violent attempt to expel it. Another, more startling theory suggests the pulsar was not born from a single dramatic explosion, but from a slower, more gentle death. If the progenitor star was being stripped of its outer layers by a companion through that ultra-fast vampirism we explored earlier, it might have expired not with a bang, but with a whisper, collapsing into a neutron star without a powerful kick. This would leave the pulsar in a tight orbit with its thief, its rapid spin a later gift from the stolen material falling onto its surface. This pulsar enigma forces a profound reevaluation of stellar death in crowded environments. Its persistent, rhythmic pulse is not just a beacon, it is a direct challenge. It tells us that the supernova process, one of the most violent events in the universe, can be tamed and contained by the right gravitational conditions. If a supernova's fury can be leashed by 7 suns, what other cosmic cataclysms are being silently managed in the dark? The rhythmic ticking of the millisecond pulsar is a beacon of order, but elsewhere in the system, a different kind of signal hints at a world of pure fantasy. Astronomers have detected tantalizing, unconfirmed evidence of a planet orbiting 2 stars within the Octuple family, a real-world candidate for a Tatooine-like world. This would be a world with not 1 but 2 suns in its sky, a place where the very concept of a day is rewritten by a complex dance of light and shadow. Imagine standing on its surface. A sunrise might not be a single event, but a staggered performance where one star crests the horizon, followed hours later by its binary partner, casting double shadows that slowly merge and separate. Sunsets would be an even more elaborate ballet, a slow fade of one star followed by the deepening twilight of the other. The planet's year, its orbit around the twin suns, would be punctuated by eclipses where one star passes in front of the other, creating sudden, dramatic shifts from day to near night and back again in a matter of hours. The immense challenge in confirming this world lies in the sheer noise of the system. Detecting the faint, periodic dimming of a star caused by a transiting planet is difficult enough around a single, quiet star. Here, the signal from the planet is buried in a cacophony of other fluctuations. The constant eclipses and brightness changes from the 7 other stars and the gravitational tugs they all exert on one another. Is that tiny, repeating dip in brightness a planet, or is it just a subtle interaction between 2 distant stellar pairs? Teasing out the planet's signal is like trying to hear a single, specific whisper in a roaring stadium. Even if it is real, the stability of such a world is a puzzle in itself. Its orbit would be a precarious tightrope walk, constantly perturbed by the gravitational tides from the other 6 suns. It might follow a wildly elliptical path, swinging close to its twin stars before hurtling out into the cold depths of its orbit, its climate undergoing extreme shifts that defy any notion of a habitable zone. The existence of this candidate pushes the limits of where we thought planets could form and survive. If a world can cling to existence in this stellar maelstrom, where else might we find life clinging to the light of multiple suns? One star in this cosmic family has a secret it reveals only every few decades. Astronomers have documented what they call the Great Dimming, a mysterious event where one of the 8 suns fades dramatically, its light dropping by a staggering amount for months at a time. This is not the clean, predictable blink of an eclipse where one star passes in front of another. The dimming is slow, uneven, and deeply strange, as if a vast, ragged shadow is drifting across the face of the star. The leading explanation is as awe-inspiring as it is destructive. Orbiting the star is likely a colossal, disintegrating world, a planet or perhaps a captured brown dwarf that is being torn apart by the star's immense gravity. This doomed object is surrounded by a titanic cloud of its own debris, a swirling storm of dust, rock, and vapor that stretches for millions of kilometers. When this vast cloud of rubble passes between the star and our telescopes, it blocks a significant portion of the light, creating the great dimming we observe. Think of it as a celestial sandstorm on an unimaginable scale, a cloud of pulverized planets so thick and wide it can veil the light of a sun. This is not a solid structure, but a natural megastructure born from annihilation. The gravitational forces within the Octuple system are likely the ultimate cause of this destruction. The constant tugs from the other 7 stars could have perturbed the object's orbit, sending it on a death spiral into an ever tighter path around its host star. Now, at its closest approach, the star's gravity is literally peeling it apart, layer by layer, creating a continuous stream of debris that trails behind it like a cosmic funeral shroud. This ongoing demolition raises a haunting question about the life cycle of planets in such a violent neighborhood. The Great Dimming is not a one-time event, but a periodic phenomenon, suggesting we are witnessing a slow-motion death of a world, a cycle of destruction that will continue until the entire object has been ground down to dust. What other celestial bodies are currently on a similar doomed path, their fate sealed by the relentless gravity of 8 suns? The silent destruction of a world is not the only strange signal coming from these stellar families. We have also detected anomalous radio whispers, structured bursts of energy that do not match the predictable pulse of a neutron star or the brief crackle of a stellar flare. These are non-thermal emissions, meaning they are not generated by simple heat, but by something far more complex and mysterious. They arrive as patterned chirps and repeating harmonics, a form of cosmic static that seems to carry a hidden order, sparking intense debate about what could possibly be creating them. One compelling theory points to an unprecedented level of magnetospheric interaction. Each star is a powerful magnet, and in an octuple system, these magnetic fields don't just connect, they can become permanently entangled, braiding together across millions of kilometers of space. As the stars move through their intricate dance, these magnetic braids are stretched, twisted, and snapped, releasing immense bursts of coherent radio energy. It would be like the sound of a colossal, celestial harp with 8 strings, its music broadcast as these enigmatic radio waves. A more speculative, yet fascinating, possibility involves the system's immense debris cloud. The vast sea of dust and gas, constantly stirred by 8 gravitational engines, could be acting as a natural particle accelerator. Charged particles, whipped to near light speed by shifting magnetic fields, might be slamming into dust grains or interacting with each other in ways that generate these structured radio signals. The entire circumstellar environment becomes a giant, chaotic radio transmitter, its output shaped by the orbits of the stars themselves. This radio anomaly forces us to confront the limits of our knowledge. We are listening to a natural process we do not yet have a name for, a phenomenon born from the unique, hypersocial environment of 8 stars living in close quarters. If the tangled magnetic fields of these suns can sing in a chorus we are only just learning to hear, what other songs is the universe playing that we have yet to tune into? That same gravitational slingshot can sometimes prove too powerful for the system to hold. Astronomers have tracked a star, a former member of an octuple family, that was not merely nudged into a wide orbit but was violently cast out altogether. This is the hypervelocity escapee, a stellar fugitive moving so fast it is on an irreversible trajectory to flee the Milky Way galaxy. Its speed is incomprehensible, over 1,000 kilometers per second, a velocity that defies the gravitational pull of every star, every cloud of dark matter, and the entire galactic core combined. This is not a runaway, it is an exile, and its path traces directly back to a single, cataclysmic event in its former home. The force required to achieve such an escape is almost unimaginable. It could not have come from a simple 3-body interaction. The only plausible culprit is the system's hidden black hole. Picture the chaotic dance of 8 stars with a dark, massive singularity lurking at its heart. If 2 of these stars formed a tight binary pair and that pair strayed too close to the black hole, a gravitational catastrophe would unfold. The black hole's immense gravity could capture one star, pulling it into a death spiral, while violently flinging its binary partner away like a stone from a sling. In this scenario, the orbital energy of the captured star is transferred almost entirely to its companion, accelerating it to a significant fraction of light speed in a single, terrifying moment. This event would have permanently scarred the system. The loss of 2 stellar masses and the immense energy transfer would have sent shockwaves through the remaining orbits, forcing a dramatic reorganization of the entire family. The hypervelocity star now travels alone, a solitary beacon of a past trauma. Its composition is a time capsule holding the chemical signature of its birthplace, a family it will never see again. As it speeds through the galactic halo and into the intergalactic void, it makes you wonder what other celestial projectiles are flying through the darkness, forever marked by the violent families they left behind. One star burns with a deceptive youth, a hot blue giant standing starkly against its 7 ancient siblings. This is a stellar paradox of the highest order, a system where one member appears billions of years younger than the family it calls home. The 7 other stars are exactly what we would expect, aging suns that have settled into the calm, later stages of their lives. Their fuel is dwindling, their light shifting toward the red. But the 8th star is a brilliant, massive blue powerhouse, a type of star that lives fast and dies young, a celestial teenager in a retirement community. This is not a case of cosmic adoption where a young star was captured from outside. The chemistry is all wrong for that. This star shares the same fundamental genetic fingerprint as its elderly kin, proving it was born from the same original cloud of gas and dust. It is a true sibling, but one that somehow ignited eons after its brothers and sisters. How can a star form so late, long after the initial stellar nursery has been swept clean? The answer points to a hidden, dormant potential within the system itself. Billions of years ago, when the first 7 stars were born, they did not consume every last bit of material. A vast reservoir of cold, dense gas remained, hidden in the outer reaches of the system, safely shepherded by the complex gravity of the octuple dance. This gas cloud was a fossil, a sleeping remnant of the system's birth, preserved in a stable orbit far from the chaotic inner stars. Then something happened. Perhaps the slow gravitational dance of the 7 older stars gradually compressed this cloud over billions of years. Or maybe a close pass between 2 stellar pairs sent a shockwave rippling through the stillness, a cosmic jolt that triggered the cloud's final collapse. Under this new pressure, the ancient gas finally reached its breaking point, fragmenting and igniting to form the single, brilliant blue star we see today. This is a starburst in miniature, a delayed and dramatic second act of creation within a system we thought was finished evolving. The presence of this youthful old-timer forces us to see these systems not as static sculptures, but as living entities with long and eventful histories. They are not just families of stars, but cosmic engines capable of reigniting their own furnaces, creating new suns long after their initial formation was thought to be complete. If one system can manage this, how many other ancient stellar families are secretly nurturing the seeds of a new generation in their dark outer halls? That deceptive stellar youth is born from a hidden chaos of invisible forces. The 8 stars are not just connected by gravity, they are entangled by a web of their own making, a vast and shifting tapestry of magnetic fields that links them all together. Each star generates its own powerful magnetic field, a protective bubble that extends far out into space. In a simpler system, these fields would remain isolated. But here, the stars are close enough that their magnetic domains constantly collide, merge, and twist around one another, creating a single, system-wide magnetic environment of staggering complexity. This is a cosmic version of a tangled ball of energized wires crackling with pent-up power. The stellar winds, the constant supersonic flow of charged particles blowing from each star, do not travel freely. They are channeled and accelerated along these invisible magnetic highways, forced into collisions that generate immense shock waves. The result is a continuous storm of space weather that makes anything our sun produces seem tranquil by comparison. These are not isolated solar flares, but system-wide magnetic tempests. A sudden reconnection in the tangled field near one star can send a tsunami of high-energy particles racing along the magnetic web, bombarding the atmospheres of its 7 siblings simultaneously. This creates a feedback loop of violence where a storm on one sun can trigger storms on all the others, locking the entire family into a cycle of shared fury. For any potential world orbiting these stars, the environment would be apocalyptic. The sky would be lit not just by multiple suns, but by perpetual, brilliant auroras dancing to the rhythm of magnetic chaos. The radiation levels would be so intense and unpredictable that they would strip away atmospheres and scour surfaces clean. This magnetic tangle reveals a deeper layer of connection between the stars, one that orchestrates their most violent outbursts and binds their fates together in an invisible, energetic embrace. If their light is a lie and their gravity a dance, their magnetic fields are the secret conversation that truly governs their stormy lives. The intricate orbital dance of these 8 stars holds a ghost in its mathematics. Careful tracking of their movements reveals a subtle, persistent anomaly, a gravitational wobble that cannot be explained by the 8 visible masses alone. The paths they trace today are the aftermath of a violent event, a disruption that occurred so long ago that no light from it will ever reach us. The evidence is written not in light, but in the persistent, slight deviations of the remaining stars from their predicted courses. It is as if they are all still reacting to the sudden, traumatic absence of a partner that vanished eons ago. This missing mass and the specific perturbations it left behind point to a single, shocking conclusion. This family was once a family of 9. The gravitational fingerprint left on the survivors tells a story of a catastrophic destabilization. Perhaps the 9th star was the victim of that stellar cannibalism we discovered earlier, completely consumed by a sibling. Or, more dramatically, it could have been involved in an impossibly close gravitational encounter with another pair, a three-body interaction so violent that it was not just slung away but utterly torn apart. Its material would have been scattered into a diffuse cloud, some absorbed by other stars, the rest ejected into the void, leaving behind no visible trace except for this one indelible mark on the gravity of its former home. This ghost star forces us to see these systems as dynamic and sometimes tragic entities. They are not permanent fixtures, but evolving families that can lose members to internal violence. The beautiful, stable hierarchy we observe today might be the calm after a storm, a new equilibrium found only after a painful expulsion. How many other seemingly stable systems in the cosmos are hiding similar ghosts? Their perfect orbits a silent memorial to a sibling that is no longer there. The ghost of that lost ninth star may be gone, but its legacy is written in the dust that shrouds the system. When astronomers analyze the spectral signature of this cosmic debris, they find a bizarre chemical riddle. The dust is not a uniform blanket of simple silicate grains like common space sand. Instead, it shows a strange and specific mixture of minerals and ices that should not peacefully coexist. There are crystals of forsterite, a magnesium-rich silicate that forms in extreme heat, right alongside vast quantities of water ice and frozen carbon monoxide that can only exist in the deepest cold. It is like finding the ashes of a volcano and the shards of a glacier mixed together in the same bowl. This impossible combination points to a history of violence on a scale we are only beginning to comprehend. These materials originate from entirely different parts of the system, from different temperature zones that should never meet. The forsterite is a child of fire, forged in the searing inner regions close to the stars where rock vaporizes. The ices are children of the deep freeze, born in the frigid outer reaches where the system's primordial comets reside. For them to be so intimately mixed, something must have shattered the boundaries between the hot inner sanctum and the cold outer darkness. The most likely explanation is a gravitational apocalypse. The same chaotic tides that create runaway stars and cannibal suns would have violently perturbed the orbits of countless asteroids and comets. A swarm of icy bodies from the outer system could have been flung inward on a kamikaze trajectory, while a family of rocky asteroids from the inner system were hurled outward. In the chaotic crossfire, these objects would have collided at unimaginable speeds, pulverizing each other and mixing their fundamentally different remains into a single, homogeneous dust cloud. This violent blending creates a unique chemical fingerprint, a signature of systemic chaos that permanently archives the destruction of entire worlds and cometary swarms. The dust becomes a forensic record, telling us that the calm we see today is a facade. This system is a cosmic battlefield, and the dust is the settled smoke from ancient planet-shattering wars. What other elemental stories are hidden within this strange, warm powder? Deep within the Octuple's grand dance, a smaller, more frantic ballet unfolds. 5 of the 8 stars are locked in a configuration so tight that they repeatedly eclipse each other from our point of view. This creates a light curve of breathtaking complexity, a signal so tangled that it looks like pure noise to the human eye. The combined brightness of the system flickers and dips in a seemingly random pattern, a chaotic stutter of shadows cast by stars crossing in front of one another. Decoding this signal is not a job for a single astronomer, it is a task for supercomputers. These machines run simulations for weeks, testing millions of possible orbital configurations, masses, and sizes, searching for the one combination that perfectly reproduces the observed pattern of light. It is the ultimate cosmic jigsaw puzzle where the pieces are stars and the picture is a flicker of light from 1,000 light-years away. This eclipsing quintuple is more than a curiosity, it is a unique stellar laboratory. Each eclipse is a precise measurement tool. When a hotter, smaller star passes behind a cooler, larger one, the way the light dips reveals the temperature difference between them. When two stars of similar size graze each other, the shape of the dimming curve maps their exact diameters with incredible precision. The gravitational tugs they exert on one another, measured through the timing of these eclipses, give us their masses. In this one tiny subsystem, we can directly measure the fundamental properties of 5 individual stars all at once, a data set of unparalleled richness. This allows us to test our models of stellar structure and evolution not in isolation, but in the violent, interactive reality of a crowded gravitational environment. The flickering light from these 5 stars is a coded message, and by deciphering it, we are reading the personal biographies of each sun, written in the shadows they cast upon each other. What other secrets are hidden in the rhythmic blinking of these celestial siblings? The constant gravitational tug of war within an octuple system does more than just warp orbits. It violently reshapes the very atmospheres of the stars themselves. The result is a phenomenon known as asymmetric stellar winds, where the supersonic flow of particles blowing from a star is not a smooth, spherical bubble, but a lopsided and directional gale. Imagine a candle flame in a room with 7 other candles, all placed at different distances and angles. The heat and air currents from its neighbors would make that single flame flicker and lean, bending its plume of smoke in one dominant direction. This is the reality for a star in this crowded family, its stellar wind sculpted by an invisible hand. The primary force behind this distortion is the intense radiation pressure from its closest stellar companions. The side of a star facing a nearby, hotter sibling is bombarded with so much ultraviolet light that it superheats the outer layers, boiling off material far more efficiently than from the shielded side. Simultaneously, the gravitational pull from that same neighbor tugs at the escaping particles, further shepherding them into a concentrated stream. This creates a stellar wind that does not blow evenly into space, but erupts in a focused jet like a cosmic garden hose spraying into the void. This lopsided loss of mass has profound consequences. It acts as a natural thruster, gradually altering the star's own trajectory over millions of years. As the star expels mass preferentially in one direction, the recoil nudges it subtly in the opposite way, a slow but steady course correction imposed by its siblings. The asymmetric winds from all 8 stars then collide in deep space, their interactions creating vast, turbulent shock fronts that glow with X-rays and radio waves, carving intricate and ever-changing cavities within the shared circumstellar environment. This relentless, directional erosion means that no star in this family gets to keep its atmosphere for its entire life. They are all slowly, asymmetrically being stripped away by their kin, their lives shortened and their deaths hastened by the very company they keep. If a star's breath can be twisted and torn by its family, what other fundamental processes are being rewritten in this stellar pressure cooker? These chaotic shock fronts are far more than zones of destruction. Within their turbulent hearts, astronomers have found a cosmic chemical factory operating at full capacity. The immense pressure and energy generated where the asymmetric stellar winds collide are forging a rich soup of complex molecules, including some of the very building blocks of life. It is a place of both violence and creation, where the raw elements of the cosmos are hammered together into more intricate forms. Picture 2 colossal supersonic winds, each a torrent of charged particles and simple atoms slamming into one another. The collision is so violent it compresses the gas to incredible densities and heats it to millions of degrees, creating a natural particle accelerator of staggering power. Within this maelstrom, simple atoms like carbon, oxygen, and nitrogen are not just scattered. They are smashed together with such force that they bond, forming hardy molecules like carbon monoxide and cyanide. These molecular seeds then act as anchors, allowing even more complex chains to form in the slightly cooler, denser regions behind the shock front. The most startling discovery is the presence of prebiotic compounds, molecules such as formaldehyde and simple sugars. These are the chemical precursors to amino acids and the nucleobases that form DNA. They are not life itself, but they are the fundamental Lego bricks from which life could, under the right conditions, one day assemble. Finding them here in this stellar madhouse is profoundly counterintuitive. We have long assumed that the calm, sheltered environments around young, solitary stars were the most likely cradles for these delicate molecules. Yet this factory suggests the opposite may also be true. The relentless chaos of an octuple system, with its constant wind collisions and shifting shock fronts, provides a continuous, energetic crucible for chemistry. It is a perpetual motion machine for molecule building, churning out complex organics on a scale that would be impossible in a quieter neighborhood. This forces a radical rethink of where the ingredients for life can originate. Could these violent, multi-star systems be unexpected nurseries for the raw materials of biology? If the building blocks of life are being manufactured in the stormy interactions of 8 suns, then the potential for life's beginnings may be far more widespread and resilient than we ever dreamed. This subtle wobble in the system's path is a whisper of something hiding in the vast dark. As the entire octuple family journeys through the galaxy, it does not travel in the straight, stately line we would expect from such a massive group of stars. Instead, its course through the void is marked by a persistent, gentle sway, a proper motion anomaly that betrays the presence of an unseen hand. Something with significant gravity is tugging on the entire system from a tremendous distance, pulling it slightly off course with every passing year. This invisible companion is not orbiting closely like the 8 bright stars. It is a distant sentinel on an orbit so wide it takes thousands of years to complete a single loop around its stellar family. The gravitational pull required to cause this wobble points to an object of planetary or substellar mass, a hidden giant lurking in the system's frozen outer reaches. It could be a super Jupiter, a gas giant dozens of times more massive than our own, but one that never grew large enough to ignite as a star. Or it might be a cold, dark brown dwarf, a failed star that radiates only a faint, residual heat invisible to our telescopes. This object's wide orbit is the key to its stealth. It is so far from the brilliant core of 8 suns that it receives little light to reflect and emits almost no warmth of its own, making it a true ghost in the gravitational machine. Its discovery was not made by seeing it, but by feeling its pull. Astronomers carefully tracked the system's position against the backdrop of more distant stars over many years, mapping a path that should have been a clean arc. The slight but consistent deviation from that arc was the only clue, a signature written in the slow drift of 8 suns across the sky. This hidden companion redefines the system's true scale. The 8 stars we watch are just the brilliant heart of a much larger domain, a kingdom ruled from the shadows by a distant, frozen giant. What other quiet giants are drifting at the edges of known star systems, their presence known only by the gentle sway they impose on the suns they command? The silent supernova theory begins with a chemical ghost story. Deep within the light of these 8 stars, astronomers have found a strange surplus of certain heavy elements, like iron and nickel, that should not be there. These metals are the ash of the most violent fires the universe can produce. They are forged in the heart of supernova explosions, the catastrophic deaths of massive stars. Yet in these octuple systems, we find these elements scattered across stars that are not nearly massive enough to have created them on their own. It is as if a crime has been committed, and the evidence is smeared on the hands of the innocent. The only plausible culprit is a supernova that must have happened right here within the family a long time ago. But where is the blast signature? Where is the neutron star or the black hole we would expect such an explosion to leave behind? This is the mystery of the silent supernova. The theory suggests that the supernova did occur, but its telltale signs were erased or distorted by the system's incredible complexity. In a normal, isolated star, a supernova is a brilliant, unmistakable event. The star detonates, outshining its entire galaxy for weeks, and leaves behind a rapidly spinning, highly magnetic neutron star that pulses for eons. But in the octuple web, the story may have been completely different. The dying star would have been one of 8, its explosion happening within a dense, pre-existing jungle of gravitational and magnetic fields. When it went supernova, the blast wave would not have expanded into empty space. Instead, it would have slammed immediately into the stellar winds and magnetic barriers of its 7 siblings. This would have smothered the explosion, robbing it of its brilliant flash and instead converting its energy into a dull, widespread heat that simply warmed the surrounding gas. The formation of the neutron star remnant could also have been thwarted. If the supernova was not perfectly symmetrical, the newborn neutron star would have received a powerful kick, shooting away like a cannonball. But in this dense family, its escape route was blocked. It might have collided directly with another star in the system. Such a collision would be an event of almost unimaginable violence. The neutron star, a city-sized object with the mass of a sun, would plow into its sibling, depositing its immense energy and its load of freshly forged heavy metals directly into the star's outer layers. The neutron star itself would be disrupted and absorbed, vanishing without a trace. The stellar survivor would be left polluted with supernova ash, its atmosphere permanently enriched with the elements of a dead sibling. This silent, smothered explosion would explain the chemical anomalies perfectly. We are not seeing the aftermath of a clean death, but a messy, cosmic murder that was covered up by the family. The stars themselves became the graves for their lost sibling, and the neutron star it became. This forces a haunting question. How many other stellar systems hold the chemical evidence of ancient, hidden cataclysms, their most violent moments erased by the very chaos that defines them? This relentless gravitational squeezing acts as an invisible furnace, turning cold, dark worlds into brilliant infrared beacons. Deep within the octuple system, astronomers have observed substellar objects that defy their nature. These are gas giants and brown dwarfs, bodies too small to sustain nuclear fusion, yet they glow with an intense and unexpected heat. They should be cold, faint embers, but instead they shine brightly in the infrared spectrum, radiating a warmth that rivals much younger, more massive stars. The source of this heat is not internal fire, but external stress. It is a phenomenon known as tidal heating, and it is a direct consequence of living in a gravitational madhouse. Imagine taking a stiff piece of metal and bending it back and forth repeatedly. The friction and stress within the material will generate heat. Now apply that concept to an entire world. A gas giant orbiting a star in this system does not follow a simple, circular path. The gravitational pulls from the other 7 stars constantly distort its orbit, stretching it into an ellipse and then squeezing it back. This perpetual gravitational kneading causes the entire planet to flex and distort. The friction generated deep within its gaseous layers and its rocky core creates immense internal temperatures, causing the world to glow from the inside out. The effect is so powerful it can turn a frozen Jupiter into a searing ball of heat, its surface temperature soaring to thousands of degrees. A world that should be a dark, frozen wasteland could instead have global, molten rock oceans beneath its clouds, churned by the unending gravitational tides. This makes these objects appear deceptively youthful and massive in our telescopes, their brilliant infrared glow masking their true identity as warmed-up planetary bodies. For any hypothetical moons orbiting these heated giants, the conditions would be both apocalyptic and strangely tantalizing. The tidal energy could power violent volcanic activity, turning a frozen satellite into a world of continuous eruptions, much like Jupiter's moon Io but on a far more extreme scale. This forces a radical rethinking of what makes a world habitable. Could the warmth for life come not from a distant sun, but from the gravitational embrace of 8? Deep within the heart of this stellar family, the erratic motions of the visible stars point to an even darker secret. the gravitational anchor holding this cosmic metropolis together might not be a single, unseen mass, but a pair of them, locked in their own intimate and terrifying dance. This is the binary black hole hypothesis, a controversial idea that suggests the system's core is governed by two orbiting voids. The evidence comes from the stars themselves, whose paths are not just gently swayed but violently jostled. Their orbits show sudden, tiny kicks and wobbles that cannot be explained by the smooth, predictable pull of a single central object. It is as if the dancers are being jerked around by two invisible partners who are themselves spinning wildly around each other. A single black hole would create a relatively stable, if powerful, gravitational field, but a pair of black holes, especially ones in a close orbit, would churn the space around them. As they whirl around a shared center of gravity, their combined gravitational field whips and twists, creating a volatile environment that constantly tugs at the 8 suns in unpredictable ways. This would explain the strange, non-repeating anomalies in the stellar motions, the gravitational fingerprints of a double darkness. The implications of this are staggering. A binary black hole system is thought to be a precursor to a colossal cosmic collision, an event that would shake the fabric of spacetime itself. To find such an engine of destruction calmly residing within a family of stars rewrites the rules of stellar system evolution. It suggests that these octuple families are not just homes for stars, but also cosmic sanctuaries for the universe's most violent and secretive objects. If a pair of black holes can coexist with 8 suns, what other monstrous partnerships are hiding in plain sight, their presence known only by the chaotic paths of the stars they shepherd? The clockwork of the heavens is not always so reliable. Within the octuple system, astronomers have made a startling discovery that the orbital periods of the tightest stellar pairs are actively changing. The time it takes for 2 stars to complete their frantic dance around each other is measurably speeding up or slowing down, a clear sign that the delicate gravitational balance is in constant flux. This is not a minor adjustment, it is a fundamental shift in the rhythm of the system itself. For a clock that has ticked for billions of years to suddenly change its tempo means the forces at work are far more dynamic than we ever assumed. The causes for this acceleration and deceleration are as complex as the system itself. In some pairs, one star is bleeding mass into space through its lopsided stellar wind or transferring it directly to a greedy companion. As a star loses mass, its gravitational grip on its partner weakens, causing the pair to spiral slightly farther apart and their orbital period to slow. It is a cosmic unclenching of a gravitational fist. In other cases, the reverse is happening. The relentless gravitational tides from the other 6 stars are constantly squeezing the orbits of the inner pairs, forcing them into ever tighter embraces. As they spiral closer together, their orbital dance accelerates, whirling faster and faster like a spinning ice skater pulling in her arms. This creates a bizarre celestial counterpoint, where some pairs are winding down while others are winding up, all within the same family. The most dramatic changes, however, are likely driven by the hidden architecture of the system. The slow, grand waltz of the 2 quadruple systems around each other creates a shifting gravitational landscape. As these massive groups swing through their own long orbits, their combined gravity can give a periodic tug to the inner binaries, either stretching their paths or compressing them, adding another layer of variation to their timings. This measurable change in the orbital periods provides a direct readout of the invisible forces at work. We are not just watching a static sculpture, we are witnessing a living, breathing gravitational ecosystem where the relationships between the stars are constantly being rewritten. If the very heartbeat of this system is unstable, what other cosmic clocks are ticking down to a final, unpredictable change? A moon in an octuple system would experience a sky of pure celestial chaos. With 8 different suns, some locked in tight pairs and others swinging on wide, lonely arcs, the very concept of a day would be meaningless. There would be no reliable sunrise or sunset, only an ever-shifting tableau of light and shadow. At times, 2 or 3 suns might dominate the heavens, their combined light casting a kaleidoscope of colors and throwing multiple, faint shadows from every rock. At other moments, the primary star might be eclipsed by a stellar companion, plunging the moon into a brief, sharp twilight, only for a third star to rise moments later and reinstate a different kind of day. The orbit of such a moon would be a gravitational roller coaster, its path constantly perturbed by the tugs of other planets and distant stars. This would create wild, unpredictable seasons. A period of relative calm with stable temperatures could be shattered in a matter of years as the moon's path shifted, swinging it closer to a different stellar pair and baking it under a new, more intense light, or hurling it out into a deep freeze. The climate would be a study in extremes, with temperatures soaring and plummeting based on a complex celestial timetable no simple calendar could ever track. And then there is the radiation. The constant stellar wind collisions and synchronized superflares would bathe the moon in a torrent of high-energy particles, making the surface a sterile, irradiated wasteland. Any atmosphere would be swiftly stripped away, and the ground would be scoured clean by this relentless cosmic weather. Yet life is tenacious. If this moon orbits a gas giant heated from within by powerful tidal forces, like a supercharged version of Jupiter's moon Europa, a sanctuary could exist. Beneath a thick, global shell of ice, a vast, dark ocean might persist, protected from the fury above. In that abyssal blackness, warmed by the flexing of the moon's core and completely isolated from the chaotic sky, who knows what strange biology could slowly, silently evolve, utterly unaware of the 8 warring suns that rule its world from an impossible distance. A faint, persistent crackle of gamma radiation has been detected from the void surrounding one of these 8 sun families. This is not the kind of energy a single star typically emits. Gamma rays are the universe's most powerful photons, born from its most violent particle accelerators. Their presence here as a faint, all-encompassing glow with no single star as the obvious culprit points to an invisible engine operating on a system-wide scale. The entire octuple environment seems to be acting as a natural super collider. The chaotic magnetic web that connects the stars, combined with the immense shock fronts where their stellar winds collide, creates the perfect conditions to whip charged particles to nearly the speed of light. Electrons and protons are caught in these turbulent fields, surfing the magnetic waves until they slam into stray photons or each other, releasing their immense energy as these faint but detectable gamma-ray whispers. This process transforms the entire space between the 8 stars into a diffuse, high-energy radiation field. It is a continuous, silent fireworks show of atomic destruction, a background hum of creation and annihilation happening on a scale we are only just learning to perceive. The mystery deepens when we consider the source of these particles. They could be the exhausted remains of stellar winds, or they might be the scattered debris from ancient, pulverized worlds and asteroids, their atoms stripped down and accelerated in this cosmic maelstrom. This gamma-ray glow forces us to see the system not just as a collection of stars, but as a single, integrated physical entity, a factory for high-energy physics whose product is a silent sleet of radiation pouring into the galaxy. If this faint signal is the signature of such powerful, hidden forces, what other energies are these systems generating that we have not yet learned to see? One star in this chaotic family holds a perfect fossil within its heart. Its magnetic field is not a tangled, chaotic mess like its siblings, but a powerful, structured, and ancient relic. This field is a time capsule, a preserved piece of the system's original magnetic character that has somehow survived billions of years of gravitational violence and stellar interactions. While the other stars have had their magnetic fields scrambled and rewired by close encounters, this one star has retained the pristine magnetic blueprint from its birth. It is a living piece of the system's infancy, a silent witness to the conditions that existed when the first of these 8 suns ignited. The strength and order of this fossil field are staggering. It is far more powerful and organized than any star of its age and type has a right to be. Normally, the churning convective plasma in a star's interior acts like a chaotic dynamo, constantly regenerating and tangling its magnetic field. But this star is different. Its fossil field is a remnant of the original magnetic field that was trapped within the cloud of gas that collapsed to form it. That primordial field was frozen into the star's very structure as it was born, and it has persisted largely unchanged ever since. How could such a delicate structure survive in this gravitational pressure cooker? The secret may lie in the star's unique history. It might be the only original member of the system that never underwent a close encounter or a merger. While its siblings were being gravitationally slapped and spun into new orientations, this one star might have occupied a uniquely stable orbit, a quiet corner in the storm where it was spared the internal churning that would have erased its primordial memory. Its strong, structured field acted as a protective cage, stabilizing its atmosphere and making it resistant to the magnetic turmoil that affected the others. Studying this magnetic fossil is like reading a page from the system's original birth certificate. The field's orientation tells us about the spin of the initial cloud that collapsed. Its strength reveals the density and turbulence of that long-vanished stellar nursery. This single star, by holding onto its ancient magnetic identity, gives us a direct link back to the very first moments of this celestial family's existence, a quiet voice telling the true story of how it all began. The dust rings encircling these stellar families are not the smooth, continuous halos we might expect. Instead, they are riddled with sharp, clean edges and vast, empty gaps, looking less like a serene cloud and more like a cosmic racetrack carved by invisible forces. This dust ring discontinuity is a profound puzzle, a clear sign that something is actively sculpting the debris, clearing lanes through the primordial material with unnerving precision. The gaps within these disks are not random voids. They are the gravitational footprints of unseen architects. The most compelling explanation points to the presence of hidden planets, massive worlds orbiting within the dust and using their own gravity to shepherd the fine material. As such a planet travels around its host star, its gravity acts like a cosmic snowplow, pushing dust and small rocks aside, clearing a wide, empty band in the disk. This creates a stark boundary, a sharp edge in the warm dust that our telescopes can detect from across the galaxy. But in an octuple system, the story is far more complex. The gravitational tides from the other 7 stars are also relentlessly plowing the disk, creating gaps and edges on a much grander scale. Each star, as it swings through its own orbit, exerts a periodic tug on the dust, pulling material into dense rings and leaving behind empty regions. The entire disk becomes a dynamic record of the system's orbital music, its structure a direct map of the gravitational harmonies and resonances between all 8 suns. The resulting pattern is a chaotic masterpiece. You might see a narrow, sharp gap carved by a single, shepherding planet, only for that gap to be abruptly truncated by a much wider void cleared by the gravitational influence of a distant stellar pair. It is a celestial construction site with multiple competing foremen, each leaving their distinct mark on the final product. This violent sculpting has a direct and dramatic consequence. These gaps and edges are the very places where planet formation is permanently halted. The dense rings might be the only safe havens where dust can slowly coalesce into new worlds, while the gaps represent forbidden zones, gravitational deserts where no planet could ever hope to form. The discontinuity we see is not a static feature. It is a live broadcast of the ongoing battle between creation and chaos. A battle where the very architecture of the system determines where new worlds are allowed to be born. Deep within the stellar chorus, one star beats with the steady rhythm of a cosmic metronome. It is a pulsating variable star, a type of sun that rhythmically expands and contracts, its brightness rising and falling in a precise, predictable pattern. This steady pulse has become the system's most sensitive instrument, a natural gravitational probe that reveals the hidden forces acting upon it. The star's rhythm is not perfectly constant. Astronomers have detected minuscule yet persistent deviations in its pulse, tiny delays and advances in its brightening schedule that occur with clockwork regularity. These are not random flaws, they are the direct signature of the gravitational tides from its 7 stellar companions. As the other stars move through their complex orbits, their combined gravity gently tugs on the pulsating star, subtly distorting its shape. When a companion star is closer, its pull stretches the variable star, making it slightly more oblong. When the companion swings farther away, the star relaxes back into a more spherical shape. This periodic stretching and squeezing directly affects the star's internal physics, slightly speeding up or slowing down the nuclear reactions that drive its pulsations. It is a continuous, gentle massage that either quickens or retards its heartbeat. By meticulously tracking these tiny rhythmic shifts against the known orbits of the other stars, astronomers can perform a feat of celestial precision. The exact amount of the timing delay reveals the mass of the star causing the tidal pull. A more massive companion creates a stronger tidal force and a greater shift in the pulse timing. Furthermore, the specific pattern of the delays across the entire orbital cycle allows scientists to triangulate the precise distances between the stars with unprecedented accuracy. This pulsating star has become a natural gravitational wave detector, its rhythmic light echoing the silent, shifting tides of its family. It allows us to weigh the other stars from 1,000 light-years away, not by seeing them, but by feeling their gentle pull on a distant, beating heart. What other cosmic rhythms are being quietly conducted by the invisible hand of gravity? The faint gamma-ray glow is a whisper from an invisible engine. These octuple systems are not just homes for stars, they are natural cosmic ray accelerators, factories that build the most energetic particles in the galaxy. The chaotic environment we have explored, with its tangled magnetic fields and supersonic shock fronts, creates the perfect conditions to boost ordinary protons and electrons to nearly the speed of light. Imagine the space between the 8 stars not as an empty void, but as a colossal and chaotic laboratory. The stellar winds from each sun are torrents of charged particles, flowing outward at millions of kilometers per hour. When these winds collide, they create immense shock waves, walls of energy that ripple through the system. A single proton caught in this turmoil can be trapped between 2 approaching shock fronts. The tangled magnetic fields act like the electromagnetic confines of a man-made particle collider, forcing the proton to bounce back and forth across the shock wave. With each crossing, it gains a tremendous burst of speed, like a tennis ball being hit repeatedly by 2 rackets moving toward each other. After countless cycles, the proton is ejected, now traveling at a significant fraction of light speed, carrying an immense amount of energy. This process is happening on a staggering scale, with countless particles being accelerated every second. These high-energy protons and electrons then escape the system, injecting themselves into the broader galactic population of cosmic rays. For decades, the origin of many of these mysterious high-energy particles has been a major puzzle. It now seems that extreme stellar systems like these could be key contributors, their internal violence seeding the galaxy with invisible, relativistic projectiles. This transforms our understanding of these families from celestial curiosities into active players in galactic ecology. They are not just passive structures, but dynamic engines, their chaotic hearts helping to write the energetic signature of the entire Milky Way. Untangling this stellar chorus requires deciphering a ghostly forest in the light itself. The rainbow spectrum from an octuple system is not a clean set of lines, but a dense, shifting tangle where the signatures of 8 stars blur into an almost indecipherable mess. Each star's unique chemical fingerprint is smeared and duplicated by the Doppler shift, the same effect that makes a siren's pitch change as it races past you. As every star orbits, its light is stretched to redder wavelengths when it moves away from us and compressed to bluer ones when it moves toward us. With 8 stars in constant motion, their spectral lines do not simply shift back and forth. They slide over and through one another, creating a thicket of overlapping clues that seems to defy interpretation. This spectral forest is a decoder's nightmare, a place where the signal of one star can be completely lost in the noise of the other 7. Astronomers cannot simply look at this chaotic data and see 8 distinct suns. They must become cosmic cryptographers, using sophisticated computer models to simulate every possible orbital configuration. They create a virtual replica of the system in their machines, assigning masses, speeds, and orbits to 8 simulated stars. Then, they tell the computer to adjust these parameters until the virtual spectrum it generates perfectly matches the tangled forest of lines we observe from Earth. It is a painstaking process of elimination that can take years, a digital excavation to uncover the individual voices in this stellar choir. Yet for all its difficulty, this chaotic spectrum is an unparalleled treasure trove. Once untangled, those shifting lines reveal everything. The amount of the shift gives us the star's velocity, allowing us to map its precise orbit. The width of a line can reveal the star's rate of spin, and the depth of the line hints at its temperature and size. In that one messy, overlapping dataset lies the complete biography of each star, a detailed map of their masses, their paths, and their relationships. What other universal secrets are currently hidden in plain sight, waiting only for the right key to unlock their meaning? These drifting clouds are cosmic nomads, belonging not to one star but to the entire system. Picture vast, shapeless nebulae of gas and dust, some larger than our entire solar system, slowly meandering through the spaces between the 8 suns. They are the ghosts of past violence, the lingering evidence of celestial destruction on a grand scale. Unlike the structured rings we find around young stars, these clouds are unbound and chaotic, their movements dictated by the collective gravity of the stellar family rather than a single anchor. They drift like colossal, silent jellyfish in a sea of competing gravitational currents. Their origins are as varied as their forms. Some are the expanding shells from ancient stellar collisions, the dust and gas thrown out when 2 stars merged and were not fully consumed. Others are the final, dissipating remains of a loosely bound object, perhaps a giant molecular cloud that was captured by the system long ago but never fully condensed into new stars. Over millions of years, the relentless gravitational tides from the 8 stars have slowly shredded this captured cloud, pulling it apart into the diffuse, wandering structures we see today. The most dramatic source, however, is likely a cascade of destruction among smaller bodies. In this gravitational pressure cooker, entire swarms of comets and asteroids are constantly being perturbed from their orbits. When these icy and rocky bodies collide, they do not just create new asteroids, they are utterly pulverized. Their impacts generate immense clouds of fine dust and vaporized ice, a fog of destruction that adds to the nomadic population drifting between the stars. This free-floating debris acts as a cosmic fog, subtly dimming the light from the stars as it passes in front of them and glowing with a faint, warm infrared light that betrays its presence. These unbound clouds are more than just remnants, they are a dynamic component of the system's ecosystem. They represent a reservoir of raw material, a floating supply of gas and dust that could, given the right gravitational nudge, one day collapse to form new stars or be accreted onto existing ones, continuing the cycle of creation and destruction that defines this 8-sun family. What other secrets of the system's violent past are written in the silent, drifting forms of these celestial ghosts? This delicate gravitational dance is shadowed by a constant, silent threat. Deep within the Octuple family, a more intimate and dangerous partnership may be unfolding. A white dwarf, the Earth-sized cinder of a dead star, could be locked in a tight orbit with a living companion, slowly siphoning away its hydrogen fuel. This theft, a quiet stellar vampirism, sets the stage for one of the most violent events in the universe. In a simpler system, this process might take eons. But here, the gravitational nudges from the other 6 stars are relentless. They squeeze the binary pair's orbit, forcing the white dwarf and its donor closer together, dramatically accelerating the rate of mass transfer. The stolen hydrogen does not simply pile up. It accumulates on the white dwarf's incredibly dense surface, compressed and heated by gravity until it reaches a critical breaking point. The result is a runaway thermonuclear explosion, a nova that can blast the accumulated material into space in a single, brilliant flash, outshining all 8 stars combined for a few fleeting weeks. Yet this spectacular nova might only be a warning shot. The true cataclysm would occur if the mass transfer continues unchecked. If the white dwarf steals enough material to push its total mass over a specific critical limit, known as the Chandrasekhar limit, it no longer has the strength to support its own weight. In a fraction of a second, the entire star undergoes a total thermonuclear detonation. This is a Type Ia supernova, an explosion so uniform and so phenomenally powerful that it can briefly outshine an entire galaxy. The energy released would be beyond comprehension, enough to vaporize any nearby planets and violently shock the atmospheres of the other 7 stars. The Octuple system would be flooded with lethal radiation, and the expanding blast wave would plow into the circumstellar debris, creating a new, short-lived nebula of supernova-forged elements. The delicate gravitational balance of the entire family would be shattered by the sudden, violent loss of one stellar mass, sending the remaining 7 stars into a chaotic reconfiguration of their orbits. This risk transforms our view of these systems from cosmic wonders into potential time bombs. The same gravitational complexity that grants them stability also creates the perfect conditions for a stellar death of unprecedented scale. What other silent countdowns are ticking within the intricate machinery of these 8 sun families? The primary star's path across the sky holds a minuscule secret. Despite the gravitational chaos of its 7 siblings, its motion is not perfectly smooth. Astronomers have detected a faint, repeating wobble in its position, a rhythmic sway so slight it is measured in micro-arcseconds. This is not the star being pulled by its close family, but the entire octuple system itself shifting around a hidden point of balance. The center of mass for all 8 stars, the system's barycenter, is not staying still. It is tracing its own tiny, elliptical path in the void. This astrometric wobble is the ghostly signature of a gravitational hand tugging on the entire stellar family from a tremendous distance. The mathematics are inescapable. To cause the entire multi-solar mass of 8 stars to sway requires a significant hidden object, and the precise periodicity of the wobble points to a single massive planet on a wide, stable orbit. This would not be a world orbiting one star or even a tight binary pair. This is a true circumpolary planet, a Jupiter-like giant whose year is defined by a single grand loop around all 8 of its suns. Imagine the sky from the surface of such a world. Its primary sun would be a brilliant but distant point of light, accompanied by 7 other, fainter stars scattered across the heavens. Their complex dance would unfold over centuries, a slow celestial ballet witnessed from a solitary outpost in a system of extraordinary scale. The existence of this world defies every expectation of where planets can form and survive. Its orbit must be incredibly wide to remain stable, placing it in the frozen outer darkness of the system, far from the gravitational turmoil of the inner stars. How it formed there, or if it was captured from the interstellar void, is a mystery that challenges our very understanding of planetary birth. This astrometric wobble is more than just a clue. it is a revelation that the domain of an octuple system extends far beyond its brilliant heart into the silent realms where single worlds can rule over 8 suns. The family portrait of 8 stars might be a beautiful lie. One of the suns in this cosmic clan could be an interstellar intruder, a celestial hitchhiker that joined the dance billions of years after it began. This captured star would not share the same birthright as its 7 siblings, its chemistry and motion telling a story of a different origin entirely. The evidence for this audacious scenario lies in the star's own trajectory and its unique chemical fingerprint. Its path through the system is slightly off, an orbital angle just a few degrees askew from the rest, as if it entered the gravitational ballroom from a different door. More tellingly, its atmosphere might hold a distinct mix of elements, a metallicity signature that does not match the shared recipe of the other 7 native stars. This star is an immigrant, its light carrying the history of a faraway stellar nursery it left behind eons ago. How could such a capture even occur? Picture a tight binary pair, 2 stars born together, drifting through the galactic disk. Over millions of years, their path brings them perilously close to the young, but already complex septuple system. The immense collective gravity of the 7 stars acts like a net. In a swift gravitational maneuver, the septuple system could capture one of the binary stars, pulling it into a new, wide orbit. Its original partner, robbed of its orbital energy, would be flung away into the void at tremendous speed, a sacrifice that allowed the intruder to find a new home. This single event would have permanently altered the system's destiny, adding an 8th member and forcing a complete reconfiguration of all the orbits to accommodate the new mass. This possibility forces a profound shift in perspective. We can no longer assume that every star in a system is a true sibling. Some are adopted, their presence a testament to the dynamic, often violent, process of gravitational socialization that occurs throughout the galaxy. If one star can be a captured immigrant, what other celestial wanderers have been quietly integrated into families we thought we understood? This cosmic laboratory of 8 suns may hold the key to physics' greatest unsolved puzzle. The extreme gravitational fields generated by such a dense concentration of mass create a natural testing ground for theories that have so far eluded us, a potential bridge between Einstein's world of relativity and the strange quantum realm. Our current understanding of the universe is built on 2 magnificent but conflicting pillars. General relativity describes gravity as the elegant curvature of space-time, perfectly predicting the orbits of planets and the bending of light around stars. Quantum mechanics, meanwhile, governs the bizarre, probabilistic world of atoms and particles. For decades, these 2 theories have refused to unite, and a key reason is the sheer difficulty of creating an experiment where both are equally important. We need an environment where gravity is incredibly strong and our measurements are incredibly precise. An octuple star system is exactly that kind of place. The complex, nested orbits of 8 massive objects create a space-time fabric that is not just curved but dynamically churning. The gravitational field at the heart of such a system is not a simple, smooth well, but a turbulent, multi-layered landscape of peaks and valleys, constantly shifting as the stars whirl around each other. This is a natural amplifier for subtle effects that are drowned out everywhere else. Imagine trying to measure how a single grain of sand disturbs the ocean. It is impossible, but in the hypergravity of this stellar family, the subtle whispers of quantum gravity might finally be loud enough to hear. One promising place to listen is around the system's hidden black hole, if one exists. According to some theories, the very fabric of space-time at the quantum level is not smooth but foamy, made of unimaginably tiny, fluctuating loops. This quantum foam would introduce a fundamental graininess to the universe, a slight jitter in the position of everything. Normally, this effect is far too small to detect. But as light from a distant star travels for thousands of years across the galaxy, passing through the wildly distorted spacetime near the octuple system's core. That tiny jitter could accumulate. The light might arrive at our telescopes with a faint, scrambled signature, a subtle blurring that betrays the foamy texture of reality itself. Another test involves the system's perfect orbital resonances. The clockwork stability of these dances, maintained over billions of years, provides a precision timer of staggering accuracy. Any deviation from the predictions of general relativity, perhaps caused by quantum effects subtly altering how gravity works on microscopic scales, would slowly build up over eons. We could, in effect, use the system itself as a cosmic interferometer, its 8 stars acting as the arms of the most sensitive gravitational wave detector ever conceived, listening for the faint hum of physics beyond Einstein. Finding even a hint of such an effect would revolutionize our place in the cosmos. It would mean that the answers to the universe's deepest questions are not hidden in futuristic particle colliders or abstract mathematics alone, but are written in the ancient, intricate motions of 8 suns, waiting in the sky for us to learn how to read them. The intricate gravitational dance of 8 suns cannot last forever. Every single orbit, from the tightest binary pair to the grandest swing, emits a faint whisper of gravitational waves, a constant, slow drain on the system's energy. This loss is minuscule, but over trillions of years it is relentless. The orbits will inexorably decay, the stars spiraling closer and closer together in a slow-motion collapse. The first to fall will be the tightest pairs, their furious dances accelerating into a final, violent embrace. Some will merge into a single, monstrous star, shining with a brief, terrifying brilliance. Others, if they are massive enough, will collapse directly into stellar mass black holes, adding dark, hungry anchors to the system's core. This triggers a cascade of instability. With the inner orbits tightening, the delicate hierarchical balance that has held for eons begins to shatter. The gravitational net that once caught runaway stars and shepherded wide orbits starts to tear. Stars on the outer edges will be slung into ever more elongated paths, their loops becoming so extreme that the slightest nudge from a passing black hole sends them flying forever into the galactic dark. The system, once a model of managed chaos, descends into pure anarchy. In the final act, the remaining core of black holes and merged stars engages in a gravitational demolition derby. They will swing past each other at unimaginable speeds, their close encounters acting as cosmic slingshots, flinging one another in all directions. There will be no single grand explosion, but a slow gravitational unwinding. One by one, the last remaining members are ejected, their trajectories set on solitary journeys across the Milky Way. The final member, perhaps the most massive black hole, will be left alone, a dark monarch in an empty throne room, its gravity holding nothing but memories. The once brilliant family of 8 suns is gone, its members scattered to become anonymous stars in the galactic backdrop or dark wanderers in the void. Their legacy is written in the elemental ash they leave behind, the iron and oxygen forged in their hearts and scattered in their deaths, which will one day become part of new stars, new planets, and perhaps new life. The ultimate fate of this cosmic masterpiece is not a monument, but a dispersal, a final lesson that even the most stable and complex arrangements in the universe are merely temporary harmonies in an endless song of change. 50 strange discoveries later, and the universe feels both more knowable and infinitely more mysterious. From stellar cannibals and hidden black holes to synchronized flares and wandering dust clouds, each revelation from these octuple star systems has forced us to rewrite a page in the textbook of astrophysics. These celestial families are more than just cosmic curiosities. They are the universe's ultimate natural laboratories, extreme environments where gravity, magnetism, and stellar evolution are pushed to their absolute limits. In their intricate dances, we witness processes we could never replicate on Earth, testing our most fundamental theories against a reality of breathtaking complexity. The universe has used these 8 sun families to teach us that chaos can have a hidden order, that violence can lead to creation, and that stability is often just a temporary harmony in an endless song of change. As you look up at the night sky, remember that these impossible systems are real, and their existence guarantees that countless other wonders are waiting in the dark, challenging us to keep looking, questioning, and wondering. We would love to hear which of these 50 discoveries reshaped your view of the cosmos the most, so share your thoughts in the comments below. The search for more of these cosmic families is accelerating, fueled by a new generation of eyes on the sky. The James Webb Space Telescope, with its unparalleled infrared vision, is peering through the veils of dust that often shroud these systems, seeking the faint heat signatures of hidden stellar members and the complex structure of their debris disks. Meanwhile, the Vera C. Rubin Observatory, poised to begin its relentless scan of the entire southern sky, will not look for octuple systems directly. Instead, it will watch for the telltale flickers and wobbles of billions of stars, creating a mountain of data so vast that it promises to reveal the anomalies, the celestial oddballs whose strange light curves can only be explained by the intricate dance of multiple suns. The sheer volume of this information is so immense that it surpasses the capacity of any single research team to analyze. This is where the journey of discovery can literally come home. Astronomers are increasingly turning to citizen science platforms, inviting people from all walks of life to help scan this celestial treasure trove from their personal computers. You could be the one to notice a subtle, repeating pattern in a star's brightness that a computer algorithm overlooked, a pattern that points to the gravitational tug of not 1 or 2, but 7 hidden companions. The universe's greatest puzzles are no longer the sole domain of professionals in observatories. They are waiting in plain sight in data streams that anyone with curiosity can help decipher. The next impossible family of stars might not be found by a telescope alone, but by someone just like you, looking up from their screen and recognizing a familiar, complex rhythm